Great, so Alexander, sir, we can start. Can we start?
Okay, yes, I'm online.
All right. Okay. Very good afternoon to all the participants. And Guten Morgen to our guest who has come all the way from Germany. Our guest for this session is Dr. Alexander Schwandt. He received his PhD from Bauman Moscow Technical University, Moscow in robotic systems and mechatronics, and he has published over 20 peer-reviewed papers. Currently, he's working in Innenbau, Gesellschaft mit Beschränkter Haftung in Germany as the head of Department of Automatization of Manufacturing Plants that help in die casting plants, press plants, SME, specific assembly processes, and additive manufacturing technologies. He has also been associated with HIDAC Software in Berlin and Robotic Center of Education and Research in BMSTU, Moscow, for development of safety critical applications of electro-hydraulic control systems of construction and agricultural mobile machines, and development of 60 tracing systems for autonomous mobile robots. We are lucky to have him, and today he'll be talking about human-robot interface based on augmented reality. So with this, I welcome you, sir, and I hand over the dice to you, sir.
Good afternoon, respected professors, ladies and gentlemen. Thank you very much for the warm greetings. Today's topic of my presentation is human-robot interface based on augmented reality. Nowadays, industrial robots are an essential part of modern production facilities, especially in small and medium-sized enterprises. But in the last decades, the demand of industrial robots increased significantly in this area. Still, a wide usage of industrial robots in this sector can't be observed. The reason can be found in increased integration costs and maintenance costs of these industrial robots, which is an obstacle for in this fast changing and small scale productions. In order to make the industrial robots more affordable for SMEs, an approach could be to improve the interaction between humans and robots during commissioning and programming processes, which would result in decreased time expense and, at the end, costs. This requires new concepts and solutions for human-robot interfaces, and in today's presentation, recently published solutions for more effective human-robot interfaces will be discussed, making an accent on practical aspects of the commissioning process of robotic systems in industry. The structure of today's presentation would be as follows, starting with a short description of the integration problems during commissioning of conventional industrial robots in SMEs. Then I would mention the boons and banes of existing solutions about the human-robot interfaces, and then I would focus more on a proposed augmented reality-based human-robot interface, where I will explain more in detail the system architecture and components of the proposed system. Then I would go more to the practical aspects of setting up this system and the calibration processes. And then the main use cases of the human-robot interface would be on a study of a gripping process, more in detail presented. Coming to the first point, mentioning the difficulties with conventional human-robot interfaces of industrial robots during integration processes in small and medium-sized enterprises. So here on the picture on the left, you see an operator teaching the robot specific positions with the tool center point of the robot and of the interfactor, where a special training is required. The usual and conventional Robot manufacturers offer 2 courses for programming a robot and operating a robot, which takes up to 2 weeks. And this means that the programming process can also only be done by special trained staff, and is quite complicated. So you see here the man is holding, the operator is holding a teach pendant in his hand, and this process is called the teach-in process, where the robot is moved by this teach pendant or a 6D joystick, what you see on this teach pendant, on specific positions, and then the positions are teached to the program or saved to the program. So it's not intuitive. So all the different coordinate systems of the robot should be taken in account by the operator, and that needs also specific 3-dimensional understanding of the movement of the robot and its coordinate systems. So the commissioning process is realized first in the first step by an offline programming phase, where in a simulation environment the program is specifically prepared. So in this environment, only the 3D CAD data of the environment is presented, and the relationship to the real world geometries are not often given in reality. So the most evaluations and the complicated commissioning process is done on the spot in the on the automated plant in factory, what we see here on this picture, and that is time consuming. So the evaluations of the process can be done only while the robot is really moving physically, and that is an error-prone process where often collisions happen or accidents. And that leads, in the result, to increased integration costs. So coming now to the second point, the boons and banes of existing solutions, I would like to mention recently a successful German startup, which is called Wandelbots. They are located by Dresden, and they follow the vision of NoCode Robotics with a so-called trace pen, which was released this summer. And we see here on the slide the commissioning procedure of a robotic system with this trace pen. The system is consisting of 2 stationary 6D tracking sensors for a 6D tracking system, which is tracking this trace pen, which you see in step 2. So the robot's working space is placed in this measurement area of these sensors of the tracking system. And in this area with the trace pen can be points and trajectories defined in 6D. So the first step is to install the sensors of the tracking system, calibrate the position of the robot in relation to the measurement system, and also the sensors to each other. This takes up to 30 seconds, as we will see in the following video. The second step would be the intuitive way of programming, where the operator is holding the trace pen and guiding it to the aimed or required positions for the tool center point to be programmed at. And in this third step, the points will be afterwards again processed, and some filtering processes will be applied for generating linear, circular, or other spline-shaped trajectories. And in the fourth step, the code will be generated specifically for this robot. Then this code will be transferred to the robot controller, and the process all in all takes, for easy applications or some standard movements, only up to 40 seconds. And this will be compared to the usual teach-in process a little bit later on in the video. The applications which can be implemented or programmed with this trace pen are gluing, deburring, inspection, welding, and also pick and place. So on the following video, on the video of the company, you will see again how these phases of commissioning in a robotic system could look like. So here we see now the trace pen on itself, where buttons are fitted, and the operator has the opportunity to teach different kinds of points. So here we see now the calibration process, where the robot will move into a certain position, and the sensors are locating their position in relation to the world coordinate system of the robot. Then it's a spike or a measurement spike will be installed onto the pen, and trajectories can be measured. You see here how points are taught or saved to the system, but also other trajectories can be measured. Then we see the after processing of the points and how the robot can manually move through these trajectories. This is everything possible to do in 6D. And then after the code generation and transferring the code to the robot is simply executing the same movement. And you see a FANUC robot and also a KUKA robot standing beside and doing the same movement. So you see it's not dependent on the robot manufacturer. So here we have a comparison of the conventional teach-in process on the left and the trace pen commissioning process on the right. So 4 minutes and 20 seconds for the conventional way and 30 seconds for the new human-robot interface. So even also for spraying applications, painting applications, also free trajectories in space can be defined. Or here also we see it for welding applications. And this is, as I mentioned already, is independent of any of the robot manufacturer. So by this, the whole programming process of the robot is much easier and more time effective. Coming now to the boons and banes of the trace pen in applications, I would like also to go more in detail about the practical aspects, how the trace pen could be used. So we see on the left side snapshot out of the video of the trace pen, where we see the working space of the robots with no obstacles. And the space is with no geometrical limitations. And on the right, we see a video of pick and place application in a multi-press plant of our recent projects. So we see how the working space of the robot is significantly limited by the surrounding machines. And hereabout, I would like to mention some critical points. The required tool center point, the working tool center point of the tool and the aimed positions can be not visible for the tracking system of the trace pen due to occlusions of the surrounding machines. Often in automated plants, the space is strongly limited. Moreover, the trace pen, when it's used, the robot body structure and the end effector position are not visible for the operator when the points are taught. We see in our hand only the teach pen, but as we see on the right picture, the gripping tool of the robot can be also complex. And by this, any collisions with the surrounding systems can happen. Then the evaluation of the trajectory of the robots for any collisions is in limited spaces, is only possible during movement of the robot. So the only evaluation possibility we have for the trajectory in the tracepan environment is the virtual environment on the pad, what the operator is holding in his hand. But there, the surrounding geometry is not taken into account. So then that's why the movement then should be done physically to check if any collisions can possibly happen. Then the last point, that's an important point, that's the time efficacy and easy programming procedure with the tracepan is significantly faster than the conventional teach-in procedure. So by on the example of this tracepan, we can see where are the pros and also the cons of this new human-robot interface. And it will save definitely in future a lot of time during the commissioning process. But there are also some other aspects which maybe can also be improved. A human-robot interface with an augmented reality environment, and which is based on a very comparable approach of the one of the tracepan, will be now also presented in this presentation in more detail. So in the following point, I would like to present the system architecture and the components of the ARhri system. The system is the interface, the augmented reality human-robot interface is added to the conventional robotic system consisting of the robot controller on the bottom left and the manipulator itself. It's implemented on a portable single-board computer and is wirelessly connected to the robot controller. For example, here we see the KRC4 controller, and the operator is actually wearing this portable single-board computer. Additionally, the operator has an augmented reality stylus in his hands and wears a variable display with a fitted camera on it. The single-board computer is here the master unit controlling the slave unit, the robotic system, the robot controller with the manipulator. And the core system of the ARhri is the reasoning system, where the movements and operations of the robots are coordinated, the programming process is guided, and also additional evaluations are implemented. So firstly, the wireless communication module is coordinating the communication with the robot's controller and also the augmented reality stylus, receiving programming commands of the stylus. This is comparable also to the tracepan, and only the implementation is a little bit different using planar QR codes. Then there is the augmented reality module, which is realizing all the where all the projection processes are implemented for augmented reality. And the operator in this case is using the augmented reality HRI as a front and is not anymore holding the teach pendant in his hand. He's only guiding the AR stylus to the required positions for teaching the program. Coming now to the homogeneous coordinate transformations in an ARhri system, the fundamental working principles will be more clearly understandable. The green mentioned coordinate transformations are the measurements which are done simultaneously by the worn camera of the operator, which is fitted on the variable display of the operator. By this, simultaneously the perspective of the operator in relationship to the robot is measured, and also the position of the AR stylus in respect to the operator is measured. Further, the red mentioned transformations are pre-calibrated or predefined coordinate transformations, which have to be set prior any commissioning process. The black coordinate transformation is actually the current robot flange coordinate system position in relation to the robot world coordinate system. So this value is well known by the control system of the robot. And what we see here is that thanks to the camera-based 6D measurement system implemented by the camera, the targeted point with the augmented reality stylus can be represented in the robot world coordinate system. By this, the operator can freely move around the robot and measure the positions and teach the positions, but moreover, it can be also used for augmented reality visualizations and projections. So what we see now are the components of the augmented reality human-robot interface. The prototype system for a proof of concept was implemented on a single-board computer, a Latte Panda, with a CPU Intel 8th generation and a 4-thread core. A dual-core system, and the operator is using a variable display on safety glasses. As you can see, the field of view of through the variable display is quite limited. It's only 12 degrees by the diagonal field of view, but it's an additional system which is not limiting the working habits and also the way how any operator could work. So it can be easily removed, so it will not an obstacle. On the picture 5 we see the augmented reality stylus, which is here like a mock-up presented and fitted with additional buttons for programming process. On the bottom right we see a marker frame, which a model of a pneumatic gripper, which is also on a 3D printer printed. It's here in this case showing how the flange of the robot with this marker frame could be orientation point for our camera-based 6D measurement system. So here on this slide we see the operator's field of view and how the augmented reality projections would be implemented in his field of view. The variable display is occluding a certain part of the operator's field of view, and the camera, which is mounted right on the same optical axis of this variable display, is reprojecting the occluded part of the operator's field of view in this display. So we see that only in this part of the operator's field of view behind the variable display is used for augmented reality projections. And in this area, we can we get an effect of optical see-through display, where additional information can be projected in, like points with the naming, the trajectories, and even also the projection of the end effector. In this case, the pneumatic gripper. This part is quite useful when the taught positions can be visualized by such an easy way. and it can be ensured that no points are lost or accidentally deleted. Even more, we get a better understanding how the robot would be positioned in each of these positions. Also taken into account the orientation of the end effector. So we see here in this picture, on the picture 8, the mock-up of the pneumatic gripper in real scale, and in point S1 to point S3, we see the virtual gripper. So we see also that it's not only a point, it's also the gripper which is rotating while moving from one point to another one. Coming now to the next and more detailed section of the presentation, that is the system setup and the calibration process of the proposed system. This section can be divided into 4 subsections. So as we were mentioning before, there are several prior calibration processes which have to be implemented for setting up the system. The 6D post-estimation is based on a camera system where mostly OpenCV is used, but also further optimization algorithms are used for further processing. So coming to the very first and most initial calibration step of the system, that is the calibration of the camera, which is essential for the position estimation. It was realized in this case with suite of the German Institute of Robotics and Mechatronics, which is an open source project programmed in the scientific programming language IDL, and it's called the programming tools are the calibration tools are CalDE, so it's the calibration detection step and the calibration lab. So beginning with the first step, there a certain pattern recognition is realized and key points are detected. That is the so-called ground truth information, which is needed for the further calibration process and defining then the intrinsic camera parameters. So in this case, it's a semi-automatic process where we see on the left picture the recognized calibration board. It's a dual target calibration board, and the points are selected manually where in consideration of the precision how it was detected. Then the images with the ground truth information, that are the point data files, are exported or imported to the call lab program, where then the camera parameter will be estimated. So there the distortion model has to be chosen, and the parameters also for the optimization algorithms, for example, for the Liebenberg-Macquart method or the simplex method, are used in this call lab program. So by choosing then, and here's it's again a semi-automatic process where we have on the right bottom of the right picture the histograms of the RMS, the reprojection error, which is presented here in the unit of pixels. And by this, points has to be deleted in accordance to the reprojection error of this picture. So by this mean reprojection error, after this calibration process of about 1 0.01 pixel can be achieved. And which then at the result will give the camera, the intrinsic camera parameters like the focal distances and the principal point of the optics, and also any distortion coefficients, which are presented here. So exactly these coefficients and intrinsic parameters are used by OpenCV and will be used in the further camera-based 6D tracking system. So here on this slide, we see a short video how the imaging process could be implemented. The key features of this implementation are that the calibration board is a larger scaled, A0 formatted, and is is designed with a dual target calibration pattern. Then the imaging positions are predefined by the robot's program and are by this also very good repeatable. And then the third key feature is the imaging process is in each position done in a complete still stand with the brakes applied. By this we get higher quality images with with no optical blurring effects. So here on this video, we see how the robot is quite fast completing this imaging process where the images are taken automatically. By this, we have about 9 to 15 images. And at the end, as I was mentioning earlier, the calibration process will be done by the two programs of the German Institute of Robotics and Mechatronics. After calibration, the analysis of camera-based pose estimation was done. So what we see here is the measurement accuracy of the camera vision system in a range from 400 millimeters to 1,200 millimeters between the measured target to the camera. The noise distribution of the coordinate components X, Y, and Z are represented on the top. And on the bottom, we see how the noise distribution, the mean value of the noise distribution is distributed on different distances between the measured target to the camera, from 400 millimeters, as I said, to 1,200 millimeters. So on a distance of 1 meter, we have finally a measurement accuracy for the X and Y axis on the bottom right table presented. It's stating 0.007 millimeters, and the angular measurement accuracy is about 1/100th of a degree. Coming now to the second subsection of the augmented reality stylus, the augmented reality stylus calibration, and the marker frame. So on the picture 8, we see that the robot coordinates system in the flange is not coinciding with the coordinate system of the orientation point. It's here only a planar QR marker. Or it could be also this marker frame, which was presented earlier. So this exact position of the marker frame, or this marker in this robot flange, should be calibrated accurately, because on this the entire measurement is depending. The same also has to be done with the augmented reality stylus, where also several coordinate systems are with these marker boards, but also the stylus tip, which is also representing the stylus tip coordinate system, the tool center point, should be also precisely calibrated in relation to the main coordinate system of the stylus. So the calibration process of the marker frame and also of the augmented reality stylus should be done only once, and in future it needs only to be the marker frame. It needs only to be installed onto the robot. So on the picture on the right we see a collaborative robot, the KUKA EVA 7, where the marker frame is installed, and on each side of the marker frame a marker board is installed, and the position of each of these boards to each other is not clearly known, and also their position in relation to the robot's flange is also not known. So for this, a series of about 30 images is taken of this marker frame from different perspectives, and the following cost function needs to be minimized for getting the exact relation of each marker board to each other. And the same is also done with the sides, the marker boards of the augmented reality stylus. But moreover, the measuring tip of the augmented reality stylus should also be calibrated in relation to the markers on its stylus. So for this, also several linear equations can be obtained, and which are also then solved by a least square estimate. So coming now to the experimental setup and experimental determination of the 3D marker frame's position in robot flange coordinate system. So once we have calibrated the marker frame in itself, we need to accurately know its position in relation to the robot's flange coordinate system. So this was experimentally done in the following setup, what we see in picture 12. The camera was stationary positioned near the robot, and the orientation point, the marker frame, was installed between the gripper, the end effector, and the robot's flange. For estimating the precise marker frame position in robot's flange coordinate system, we should consider first how the robot flange coordinate system is set up. On the picture 13, we see how the coordinate system is orientated, and we should take into account how the kinematic joints are set up for such an angular manipulator. We see on the picture 13 the wrist of the robot that are three intersecting rotational axes. That's the A4 axis, the A5, and the A6 axis, which are mostly needed for obtaining specific orientation of the tool in the robot's work environment or workspace. The axis Z of the robot flange coordinate system is in this case coinciding entirely with the A6 rotation axis. So that's the last dimension of freedom of the robot, the last joint. As well, the axis Y of the robot flange coordinate system is coinciding, is parallel with the A6. That's the second last rotatory axis of the manipulator in its wrist. And by this, a so-called circle point analysis method can be used to re-identify these coordinate axes in a specific position. So the calibration process is divided up into 3 stages. The first stage is to measure the starting position of the marker frame and track the current robotic joint position, every drive. The second stage is to move the joints of the robot sequentially, beginning with the last one. So the first rotation would... Excuse me? Yes. So the movement is starting with moving the last joint by rotating around the z-axis of the robot flange coordinate system. That will lead into approximately circular trajectory, which is measured by the camera system, and then the A5, the rotation around the y-axis is executed. And in the picture 14 in the top right corner, we see the experimental data, which is measured. So the one corner of the marker board was taken into account, and by moving this side of the marker frame around the A6 axis, the z-axis, we got the trajectory in blue, mentioned with the letter C. By moving around the A5 axis, we got the circular trajectory around, which is mentioned with the point A. And where these two circular trajectories are intersecting, we see the starting point. So that is the aimed position, which we are going to measure in relation to the identified starting position of the coordinate system of the robot flange. So out of these two trajectories, the coordinate axis mentioned with B and D are estimated. By this, we have then, which is presented in table 1, the identified marker frame position in robot's coordinate system which is called flange. Yeah. So coming more in detail about the circle point analysis, it's an iterative optimization process based on Gauss-Newton iterations. Roughly saying, it's divided into the following steps. First, circular trajectory consisting of several hundred measurement points. In the first step, the rotation plane in 6D in the working area, working space of the camera is estimated by a least square estimation, and then the center coordinates of the rotation axis in this rotation plane is approximated. Then the squared error of the we see it on the second picture on the right, the squared error of the rotation center in this rotation plane is minimized by linearizing it in relation to the first approximation. So at the end, we get in 3D the position of the center of the rotation, and also the orientation of the rotary axis. So by this, the conversion behavior of the Gauss-Newton iteration-based CPA method, where with this experimental setup as follows, we see on the left in picture 15 the maximum square error in relation to each iteration, where we see how fast it converges towards the squared error minimization. And on the right, we see the correction signal for the X and Y coordinates in the rotation plane. The conversion criteria for the iterative circle point analysis method were as follows: that the points of where the squared error exceeds the threshold of 90% of the maximum error are deleted, and the least amount of points after deletion should be more than 100. And at the end, we got an astonishing good precision of the calibration of the minimization process. And by this the exact position of the flange robot coordinate system was estimated during the initial measurement of the marker. And by this, the T marker coordinate transformation, as we see it here on the picture 8, could be defined clearly. Then I would like to come to the implementation of the augmented reality human machine interface module communication with the industrial robot controller KRC4, where I would like to present more practical aspects of the implementation, how the communication is implemented with the e-key interface, the Ethernet communication interface, specifically for KUKA, and how it can be used also for other applications. So what we see on this schematics are the block schemes of calling subroutines, and also what information is sent from the communication module and the robot controller. The single board computer, where the augmented reality human robot interface is implemented, is serving as a server, and the robot controller is in this case the client. The augmented reality human robot interface system is sending to the robot points and trajectories where the robot has to move to. And on the other hand, the robot system, the robot controller, is sending positions, torques, speeds, and also the states of the brakes to the server. But I would like to go more into detail how the e-key interface is implemented and working in the KUKA controller. So on the highest level, there's the SPS sub script, which is executed by submit interpreter cyclically every 50 milliseconds, but that is a parameter which can be set. And by the cwrite run function, SRC script will be called. It's in this case, it's named main logic, where the threads for receiving and also for sending data are coordinated. The access to system variables, for example, positions and torques and speeds in the system set can be accessed. So they are called system variables in this case, of KUKA. And also the robot movement functions are called in this SRC script. Then, thanks to the script, the threads for sending and receiving, for the sending and receiving channels are controlled, which are here channel 1 and channel 2, where the IP is in this case static, and the port is varying every time because of any renewing process of the connection. This case is very specific to KUKA, where the port somehow is changing frequently. But yeah, this should be discussed a little bit more detailed in another moment. The Ethernet-based protocol is in this case the TCP/IP protocol, and by this, every 50 milliseconds, the robot is accessing, getting new information and executing new programs, program points. So coming now to the more practical aspects of the augmented reality-based human-robot interface, where I would like to discuss the main use cases of the human-robot interface. In this case, we are more, spotting or focusing more on a gripping process of die-casted parts. So, for comparison, here we see the conventional teach-in method, where on the left picture we see an operator, which is, again, as we saw it also on the first slide, teaching the robot specific positions for execution welding process. The first step is the preparation of commissioning with, for example, Orange apps, and that's the offline programming method, where we see in the small picture the simulation environment. And then we step into the second step phase, where the commissioning is done on the production facility. So that's an iterative process during the commissioning, where the points are corrected in accordance to the surrounding geometry. Then the trajectory and movement of the robot will be reviewed, and the final cycle time is checked afterwards. By this, our customers have mostly very short cycle times to be implemented. And that's for the trajectories and points has to be corrected several times, and this is time consuming. So by this, often can also collisions happen, because the robot can, for example, slide over points with interpolation radius, not going through every point with hard stops. So by this, the movement of the robot can be sometimes unpredictable in limited working spaces. So the last point, the main use cases of the augmented reality human-robot interface is divided up into three main use cases. It's the robot's program visualization, then the visualization of robot's movement, and then also the virtual programming by demonstration method, which is in this point a new aspect. And is comparable to the well-known programming by demonstration method. Let me start with the robot program visualization. As we saw it already on a prior slide, here we see how robot's program can be visualized to the operator. The points, it's an important fact that the points of the entire program are visible to the operator in real scale in the real world environment. Often the problem of our commissioning processes of our automated robotic systems is about the precision of our pre-configuring our automated plant, meaning that when we program offline a robot in our CID environment, a simulation environment, it doesn't mean that the real position of our machines at our customers are correct in the same way. And often we face the problem that on the limits of robots' range or in very limited spaces, we have only tolerances of about 5 millimeters, where the robot has to pass with full speed to achieve the needed cycle times. So the advantage of using augmented reality in the human-robot interface is that only additional information and geometric shapes has to be projected into the real-world environment. So we are taking the entire real-world environment into account, but using the augmented reality for more informative view to the operator. By this, the operator can freely move around and has the same visual capabilities as it would be in a simulation environment. But here it is happening in real world. So by this, we achieve a less error-prone commissioning due to the visual program overview. Often it happens that program points are accidentally removed, deleted, and then the robot would just straight execute the movement from the one point to the next one by colliding and maybe damaging machines. Or even the human can be in danger in this situation. So the next step would be also the visualization of the robot's movement. The robot's movement in this case is done only virtually. By these three images, I tried to show how the visualization could look like. Here we have a gripping process of a die-casted part of a transporting system, of a conveyor, and it's a very simple trajectory consisting of 3 points and 2 linear movements, where the gripper is projected into each position. By this, the real robot is physically can be switched off, and only virtually the gripper is moving towards the aimed target. By this, the entire movement can be observed from different perspectives, where maybe also any collisions can occur with the surrounding geometries or machines. This approach is easing up the entire visualization and understanding of the process, and increases also the safety for the operator, because often it happens also that robots are doing unexpected movements due to complex program structures with interrupt programming and subsequences, where it's not always obvious what the robot is going to do in the next step. Moreover, it should be also mentioned that in the most of our robotic systems, the space is very limited between the robot and the surrounding geometries. And even when the operator is also working in this environment, it should be well known what the robot is doing next, because it's not possible to escape from the robots when it's moving fast. So coming now to the last and main use case of the augmented reality human-robot interface, it's the virtual programming by demonstration. It's in this case very similar to the prior mentioned trace pen, where we see here on this picture on the bottom right corner the well-known programming by demonstration method, where the end effector and the robot are physically guided by the operator, and the program is written or traced, I would say, by measuring continuously the current joint positions of the robot. By this, complex movements can be easily programmed by guiding the robots through the aimed points, but it's also error-prone, meaning that the accuracy of programming such a trajectory is decreasing by twice as the position accuracy of the robot is capable. That is because measuring the position of the robot in a certain position by its own sensor system is happening according to the certain tolerances of the sensoring system. But again, when the program is executed, the same sensoring system is used for reaching this position. And by this, an external, more accurate measurement system, which could be, for example, in this case, also a camera-based 6D tracking measurement system, could compensate these tolerances in the first programming step. So what we see on the left part of this slide in the picture, there we see the augmented reality stylus, where the virtual end effector or gripper is projected onto the augmented reality stylus. So what the operator sees in his variable display is not the augmented reality stylus, it's actually the virtual gripper. So he's easily saying he is also guiding virtually the robot by its end effector. And that's why this programming method could be called virtual programming by demonstration. Even here, the robot is completely switched off, and the teaching process is done intuitively, just by guiding the virtual gripper to the aimed points. Additionally, we see also the X, Y, and Z coordinate components of the current augmented reality stylus tip in relation to the robot's world coordinate system, and also the three Euler angles A, B, and C of the KUKA notation. Additionally, we see also here the program gripping this die-casted part consisting of these 3 points. And by this, we see also how easy and the programming process could be as it is implemented with a trace pen, but with the small benefit of the augmented reality technology, where we get an understanding of how the virtual gripper would be placed in this working space or in this situation in accordance to the surrounding limitations. What I should also mention is that in bigger automated plants, for example, in automated riveting plants, the end effector could be also of bigger dimensions, weighing about 250 or 300 kilograms. And in this case, it is simply not possible to implement this programming by demonstration method by moving this big end effector weighing 300 kilograms physically to the aimed point. So by this, projecting virtually bigger sized end effector onto the AR stylus would lead also to easier handling and also better understanding of the program. So here once again also summarized the advantages of the intuitive virtual programming by demonstration. It can be used by less experienced staff, as it was also with the trace pen. The programming procedure is much faster, and the fine-tuning is easier. The operator's safety is significantly increased, since the robot is entirely, it's switched off and doesn't have to be moved at all for any validation of the program. And the understanding of the program is also much more understandable for the operator, since to the augmented reality technology. So coming to the limitations and also the future projects, I would like to outline that the operating range of the augmented reality human-robot interface is defined by the measurement or operating range of the camera-based 6D tracking system. And by this, we are talking about a limited range with in a radius of 2 meters, meaning that bigger scaled industrial robots, working areas of which are in a radius of 3 or 3.5 meters, sometimes would be complicated. It can be combined where with the robots controller, where as we were saying earlier, the marker frame would be taken as an orientation point, but in this case, further considerations should be done about measurement tolerances and taking also the positioning tolerances of the robot into account. The limited area of view of the coverage, covered by the variable display can be also an issue. So the solution presented here is a low-cost solution with a variable display of the company Viewfine, a startup from California, and costs only $200. So in this case, the implementation of this interface is affordable for SMEs, but this limitation of the limited area of field of view is definitely a point what should be improved. The entire structure of the manipulator should be also visualized for making any collision checks during the previews of the robot's movement. Meaning that, as we saw earlier on a picture where a multi-press plant robots were executing a pick-and-place application, even the elbow for the robots or other parts of the robots, like for example a dress pack or any other tubings on the robot, could collide with the surrounding geometries. What should also be projected into the AR environment. And for this, further work has to be done, which is also currently also worked on in my university. Then the fourth point is the projection errors occur due to the lack of depth information in case of partly occlusions. What's this camera-based 6D tracking system is lagging off is the depth information, which leads also to effects where occluded objects appear in front of any other surrounding geometries. And this can lead also to misunderstandings for the operator working also in limited or working spaces with the robot. The cycle time estimation simulation of the robot's motion should be also implemented by a dynamic model of the manipulator, which will not only static or virtual show the movement of the robot, but also taking the physics behind the robot's movement into account. So this is essential since our customers are mostly taking into account the final cycle time of the automated plant. So coming to the conclusion, the intuitive virtual programming by demonstration method is time-saving and usable for less experienced staff during commissioning of industrial robots in small and medium-sized enterprises. The programming procedure is much faster, and the fine-tuning is also better visualized and easier possible. And the safety aspect for the operator is increased. The review of the taught program to the robot and the entire commissioning process is also faster. And due to the limitations which I stated earlier, the development or the further development of the augmented reality ARhri is definitely required and will be later on also represented, what we are currently working on. So finally saying, after the conclusion, is that there are several companies working now also on augmented reality technology as interface for human-robots interaction. And as we see, one successful approach by teaching industrial robots with a trace pen was shown now with the startup Wandelbots, and even also other bigger companies like ABB are also showing their augmented reality solutions to their customers. But they are using it more as a planning tool for setting up layouts and machine positioning in their plants. So thank you very much for your attention. I hope I answered for a lot of questions, but still I'm also excited to answer now on your questions. Thank you.
Thank you, sir. Participants, are there any questions on your side? Yes, participants. So I have one question, if I may.
Yes.
So when can we expect augmented reality robots in your general use in human life, at home use, sir?
Yeah, so this is actually not such far dated target, I would say. So as soon as as robots get cheaper, in theirs obtaining them in private usage, they would also be easily controllable by these augmented reality human-robot interfaces. So we observe now that several companies are implementing augmented reality technologies in their app. For example, IKEA, where through a phone or a tablet, furniture can be chosen and placed into your living room, and you can understand how it will suit there or in another way. And the same also would happen with robots. We see that mobile robots are already used for vacuum cleaners. And for this, the robots, they got cheaper, and the augmented reality is already capable of programming such robots, for example, in kitchen applications, cleaning applications, or tidying the flat. So it's mostly a question about price.
Okay, thank you, sir.
Yeah.
Participants, do you have any more questions? I think there are no more questions. So with this, we'll end the session. I thank you, Dr. Alexander Schwandt, for this wonderful session that we had on the augmented robotics and their augmented reality in robotics. If all the participants can wait, we'll just start with our valedictory function. So we are starting with our valedictory function. And for our valedictory function, I would like to welcome all the participants that are present, also the staff, the faculty members that have joined us. I would also like to welcome the HOD of our department, Dr. KB Sutar sir, who has also joined us here for this faculty development program. We have finished about 16 sessions in the last 5 days, covering a wide range of topics on various robotics and their application. So it was a wonderful session, and if we could have at this moment a few of the feedback from the participants, that would be nice. So any participants, would you like to give the feedback on this session? Yes, any participants? Mr. Apurva Roy, would you like to please give us a feedback? Your voice is a little low, sir, if you can.
Is it okay now?
Yes, sir.
Good afternoon, sir. Myself, Apurva, and I'm from computer science background. Still, I did register for this.
Your voice is not audible, Apurva Roy, sir. Your voice is not audible. If you can check your mic, I think your voice is not audible.
Hello.
Yes, sir. It's audible now.
Okay. Myself, Apurva Roy, and I am from the computer science background, but still I dared to register for this course. I just understood that this robotics, though it is organized by the Department of Mechanical Engineering, but still I have something to learn from that course. And after the end of this, 5 days workshop, I can say I have rightly thought, and I have just gathered some concept at least with which I can just proceed in future and just work in this field of robotics. And obviously, many speakers, those actually just given their valuable lectures, and I must agree that I may not able to understand everything as because I am not from the mechanical background, but still I have got the basic idea from all these sessions, and I think not only me but for all participants also got that essence of the course, and I think many of them will be the benefited from this course. I thank you, the organizer, for giving me the chance to participate in this workshop. Thank you, sir.
Thank you, sir. Thank you for that wonderful feedback. Anyone else? Mr. Vishal Bhagwat, sir, would you like to give us a feedback? Bhagwat, sir? Anyone else? Any participants apart from Bhagwat, sir, would you like to give us a feedback? Okay, so Moving forward, I'll just present to you what we happened in this entire FDP. Our FDP started on the 24th of November 2020, and we had lined up a lot of faculty from. We had lined up a lot of speakers from various institutes like IITs and NITs, institutes of national importance, as well as we had some speakers who had come from the industries. There were some scientists who had discussed various topics. So on the first day, we had Dr. S.K. Saha, we had Dr. S.S. Ohol who were present for inauguration. And after that, we had sessions from them. We were introduced to innovations in robot technology by Dr. S.S. Ohol, sir. After that, we were given the introduction of robotics by Dr. Ravi Mandava, sir. And at the end, we had a company person who was director and the CTO of IndiaSoft Technologies, Mr. Praveen Bell. He gave us the introduction to an automation studio software, the software that is used by various robotic companies, and what can be done using those software was given to us. The next day, we had another personality from the industry. We had Mr. Sunil Gokhale, who is the CEO of Awesome Technologies, telling us about the research opportunities that are present in robotics. And then we had a professor from MNIT Jaipur, Dr. Rajesh Kumar, who gave us a quick glance of what is robot motion control and how do we control them. Towards the end of the day, we had another person from the industry from Eton Aerospace, Mr. Anil Ambore, who actually showed us the use of Automation Studio in industry. The previous day, we had learned the introduction. We had given the introduction to Automation Studio, and the next day, we learned how that Automation Studio is used in industry. On 26th November, the third day of our FDP, we had Dr. S.K. Saha, who came again and showed us the various technologies of robotics which are useful in the rural setup, how robotics is going to change the face of rural India. That was what he discussed. Unfortunately, we had a cancelled session from Dr. Vasant Rajgopal, who was actually based in Tamil Nadu, and he faced problems due to the cyclone there, and he could not connect with us. And unfortunately, due to the busy schedule, we could not reschedule him. And at the end of the day, we had a session from Dr. Ravi Kumar Mandava again, who gave us the design of PID control for robotics, how to control a biped robot using the PID controllers. Friday, 27 November, we began with modular robotics for industry, another good session in which you could assemble various robots that are required for Industry 4.0. This session was given by Dr. Ekta Singla, who was associate professor at IIT Ropar. In the afternoon session, we had a wonderful session by SVR Infotech. The key people there were Mr. Vinod Atpalkar and his associates, who gave us a glimpse of robot programming. How do we program a robot using various languages? That was given to us. And then we had Dr. Tushar Kanti Bera, who actually showed us how we could apply electrical impedance technology for studying artificial skin in robotics. So how our robotics could be covered by skin and how that skin would react to various forces that were present. That was given to us, which was an interesting session. And then we had the last session yesterday by Dr. S.S. Ohol, sir, who told us about social robotics, how robotics are integrated into the lives of human beings at various levels, in hospitals, in home, and many other places. He gave us a lot of videos that show these robots and how they are helping us, the mankind. Today, on the last session, we had very eminent personalities speak to us. We had in the morning session, we had Dr. Ashish Datta, who told us about hands and legs exoskeleton and how we use them in robotics. We had another scientist from Baba Atomic Research Center in Mumbai, Dr. Debonik Roy, who told us about web-mediated robots and how they are the future. And lastly, but not least, this wonderful session that we had from our chief guest, Dr. Alexander Schwandt, about human-robot interface, which was based on augmented reality. So that summed up all the FDP that we had. We had very good speakers, and I think it was a very good FDP. With this, I would now like to call our HOD, Dr. KB Sutar, sir, to address the gathering.
Thank you, Ashwin. Good afternoon, all. I welcome with chief guest for this directory. He delivered a wonderful session on human-robot interface and augmented reality. He was also an expert for our online FDP on advanced manufacturing processes. Sir, since June 2020, in about last 6 months, our department has organized 4 FDPs through online mode. The first FDP was on nanotechnology. The second one was on advanced manufacturing processes. The third one was on energy technologies, and the current FDP on robotics and automation. My sincere thanks to AICTE for approving our proposal for online FDP on robotics and automation. And they have given us the opportunity to conduct this FDP through AICTE training and learning, that is Atal Academy. Due to COVID-19 situation, our physical movements are restricted, but we can definitely interact with each other through such online FDP. I am very fortunate to have young and dynamic faculty members and colleagues in the department who handle the responsibilities very efficiently. Though we have 25 faculty members in the department, for each of these FDPs, only a group of 5 to 6 faculty members is actively involved for all planning and execution along with me. I must appreciate the efforts of our faculty members, Mr. M.K. Beldan, Mr. Ashwin Nayak, Mr. Yuvraj Thorat, Mr. Sanket Unde, Mr. Shekhar Shinde, Mr. Akshay Harare, Mr. Dadaso Mohite, and Dr. D.G. Kumbar for actively working very hard for making this FDP possible. I am confident that the participants have learned many aspects of robotics and automation wherein they can undertake the research activities. Thank you so much.
Thank you, Dr. Sutar, sir. I would now like to call upon our chief guest for this valedictory function, Dr. Alexander Schwandt, to please address the gathering. Dr. Alexander Schwandt.
Yeah, thank you very much for this warm greeting and also the opportunity to take part in to this valuable FDP program. The FDP program is mainly also about interaction between industry and science different science institutions, which is in my point of view also very important and very good also for the any development on both sides. So industry needs new scientific approach, but also on the other hand, the actual problems of industry should be taken into account in any scientific works. So in this case, I also very thankful for the valuable informations what I got in a wide range of topics, which are also not so well known for me. So that's why it was very informative. And thankful that I could take part, also to provide any information for the FDP program. So in this case, I think this is a very valuable method of organizing knowledge and transferring knowledge, and get into communication for further development on both sides. Even that we are now in this pandemic time a little bit limited about our communication capabilities, but I think the solution today was a very well process. So that's why thank you again for this nice opportunity.
Thank you, sir. Thank you for your interaction. It's very nice of you to join us from Germany, and that gives our FDP a very nice glow, I can say. So with this, we'll finish the vote of thanks, and to finish the valedictory function, I call upon Professor M.K. Beldar to present the vote of thanks.
Thank you, Ashwin. Good evening to the Honorable Chief Guest, Dr. Alexander, respected Head of the Department, Dr. K.B. Sutar, all the teachers and participants. I am Professor ARhri Beldar, would like to take this opportunity to express the vote of thanks. At this occasion, I must remember our beloved Founder Chancellor of Bharati Vidyapith DMTB University, Dr. Patangrao Kadam Sahib, who is the constant source of inspiration for all of us. My sincere thanks to the Chancellor, Professor Dr. Shivajirao Kadam, Pro Vice Chancellor Dr. Vishwajit Kadam, Vice Chancellor Dr. Manikrao Salunke, and Principal Dr. Anand Bhalerao for their constant guidance and support, which help us to organize such kind of FDP. Also, my sincere thanks to AICTE for providing the funds to organize such FDP through AICTE Training and Learning Academy. Now, I sincerely thank our chief guest, Dr. S.K. Saha from IIT Delhi and Dr. S.S. Bhol from COEP for kindly accepting our invitation and gracing the inaugural function. I am also thankful to Dr. Alexander Schwandt for accepting our invitation to be the chief guest for the valedictory function. And most importantly, I thank all speakers from different institutes and industries for giving valuable time and their session. I am thankful to all the participants for registering and attending this FDP. Without your active participation, program could not be successful. I shower my heartfelt gratitude to the head of the department, Dr. K.B. Sutar, for constant support and motivation for this FDP. Also, thanks to all professors from the Department of Mechanical Engineering and everyone of Bharati Vidyapith family for their wholehearted support rendered in the success of faculty development program. Thank you very much.
Thank you, sir.
Thank you, sir. With this, we end the valedictory function. There's a list of instructions for the participants. Participants will have to fill the feedback form, which will be sent to you shortly. Apart from that, you'll have to fill the feedback form on your ATAL login also, the ATAL Academy login. You'll have to fill the feedback form there as well to get the certificate. Your certificates, you'll get your certificates on your ATAL FDP login site only. All right. So if you fill the feedback forms, only then you're going to get the certificates. So do not miss that. The feedback for today's session will be sent to you shortly. Thank you.
Thank you, sir. Thank you very much.
Thank you very much.
Thank you. Thank you, sir.